Thank you, Heather, and thank you everyone for being here today. My name is Thomas. Thomas, if you want the hard mode French pronunciation, and I will indeed be talking about Active Directory today, and more precisely on how, as cyber responder, we can uncover persistence implanted by threat actors. A few words on myself first. I do incident response at Weston, which is a French consulting firm. I also do stuff on the more offensive side, mainly pen test and red teams with a focus on Windows and Active Directory environments. And I try to contribute to open source projects such as EDR Sunblast, a tool I developed with a colleague, and Farsight AD, a tool that I'm introducing today. So I guess most of you are familiar with what Active Directory is. A very quick reminder nonetheless. Active Directory is a Microsoft directory services that handle authentication and authorization across an organization. It can mostly be used to, well, mostly, it can notably be used to administrate endpoints, Windows endpoints, and is in that regard often considered to be the keys of the kingdom. It's been challenged in the recent year by Azure AD, which is a completely different product, but it's so tightly imbricated with on-prem networks that it's most likely here to stay for a little while longer. So why should we care about Active Directory security? You have here an example of a ransomware incident that occurred in 2020. And it showcased quite well how ransomware operators can leverage Active Directory to elevate the privileges and deploy their ransomware payload at scale. Very standard classical techniques here with remote initial access from a Citrix farm exposed on the internet, and then exploitation of a vulnerability on an unpatched system, followed by a lateral movement, first with a local administrator account mutualized on various systems, and then with increasingly privileged domain accounts. What's interesting here is that between the time the attacker had obtained domain admin privileges and the time the ransomware payload was deployed, the threat actor took around a week to snoop around and exfiltrate confidential information, or what they thought were confidential information at least, but they could also have used that time to deploy persistence to come back more easily in the environment, for example, if the ransom was not paid. It's an example, but there are many others for the past few years. So yeah, Active Directory, as being the keys of the kingdom, is quite often targeted in ransomware operation. Let's now say that we are incident responder on that incident, and we are working on the forest recovery part. We would have two options, really, to recover the forest. The first one would be to rebuild from scratch, which is something that can be done on smallish domain. But as this incident happened on a domain with thousands and thousands of endpoints and users, that would just not be possible, not practical. So we would have to go the second option, which is to use either backups, if they are not encrypted, and if there are backups, of course, or to use the current state of the Active Directory domain. To do that, we would shut down all domain controller except for the PDC, place that PDC in an isolated network, and replicate data on the newly promoted domain controller. At this step, this is where, as incident responder, we can help. Because before going back live in production, we would have to clean the Active Directory domain, identify and remove any eventual persistence left by this threat actor. To do that, we would have a few challenges. The first one would be the lack of historical information. As anyone that has done commercial incident response may know, if logs are not centralized from domain controllers, and it's often not the case, you have very little historical data as the logs rotate very quickly. So you may have only a few hours of historical data in the security event logs. And even if you have more data, even if the logs are centralized, it's often only authentication logs, like very basic or Kerberos, very basic authentication success, failure, or Kerberos ticket requests. So while those are great to map lateral movement, they are not enough to precisely identify persistence. And the last thing is, it's often also the default audit policy that is enabled, which offer a good baseline, but is missing some key events to map and identify persistence. Everything not lost, however, as we have a few ways to retrieve some historical data. The first one is to AD replication metadata. A replication is a mechanism used by domain controllers across a domain or forests to replicate data and have a common set of objects. Without much privileges, only standard user privileges, we can retrieve replication metadata about the replication operations that occurred. And this metadata can give us information on the last time an attribute was modified and the last value the attribute took. I'm not going to go into too much detail here, as there is a lot of material in the deck and in the presentation. It's a subject that has already been covered, notably last year in the DFIR summit here, with the AD Timeline, a tool developed by the French agency to make a timeline from this replication metadata. There are 2 more slides in the deck that are hidden currently, because, so if you want more detail, you can look at the published slide. But yeah, as I had to meet the 40-minute time frame, I can go into too much detail here. Another artifact that can help us to identify compromised accounts this time is the user access login. This artifact has been put in the spotlight quite recently, as it's enabled by default and has 2 years of historical data. Compared to the few hours we may have from security log, that's huge. Through this artifact, we can track access to the Windows Server roles. So for instance, we can track access to the Active Directory Domain Services role, which is the AD role, basically. And we can retrieve information on the client username and client IP accessing this service. This artifact is of great value to map lateral movements and also identify possibly compromised accounts, so it can help us focus our research for persistence. And finally, another way we can follow to identify persistence is to query the current states of the objects. There are tools that do that, most notably Bloodon, a very famous one to identify a compromised path, and Ping Castle, more on the security audit side. And we can use those tools to quickly enumerate information about the objects and have an evaluation of our security level. Those tools are particularly useful in the hardening part of the forest recovery, because we want to identify persistence, of course, but we want also to make sure there is no easy way for the attacker to come back and elevate its privilege again. But while those tools are great, they are not specifically aimed to identifying persistence. They are more aimed to evaluate your security level. That's why I developed Fairsight AD, which is a tool that enumerates the current state of the domain to identify anomalies and retrieve as much timestamp as possible through AD replication metadata. It's a PowerShell toolkit that produces either CSV or JSON files for manual analysis, for example, using Timeline Explorer, or to be sent in your CM of choice. But before jumping right into identifying persistence, we have to make sure that we have access to the right data, that we can see all objects. Because in Active Directory, it's possible to hide objects using specific access rights. So for example, by setting read property denied access right, it would be possible to fully hide an object. Well, if you only set, and there is a demo showcasing that just after, if you only set the deny access right to read properties, the object can still be listed from its organizational unit of residency. But it's also possible to prevent listing of children objects on that organizational unit so that the object is completely hidden. We have a quick demo here showcasing that. So first, a new organizational unit is added in the domain. A new user is added as well. And as we can see, we can retrieve all attributes of this object. Now we are setting a deny right on the object. And so we can no longer find this object. We can no longer retrieve any of these object attributes. We can, however, as you can see here, list the children of the organizational unit this object lives in to retrieve, to see that we have an object here. But second comment here, it's possible to prevent that, to deny the listing of children, and we can no longer see our object. So if we only query the current state of the domain, we may miss some fully hidden users. There would be another technique that threat actor can use to hide not this time completely an object, but only specific attributes, so that instead of having a fully hidden object, there is only attributes related to persistence that can be hidden. We will have a demonstration here showing how we can do that with the SID history. So I'm going to go into more detail on the SID history in just a bit, but we are going to showcase here how it's possible to add an SID in history, which is not something that can normally be done. So it's something that is done through a DC shadow attack, and how we can hide this history so that it's no longer possible to retrieve any of the SID configured in history. And if we do that, there would be no difference between a user not having any SID in history and a user having an SID in history, but with prevented listing. So here we are doing the DC shadow attack. So, well, it's an attack used to impersonate a domain controller and conduct operations that will normally not be doable. And we can now see that our user has an SID in history. If we prevent listing of the SID history, and we do the query again, we no longer see the SID here. So it would be completely possible for a threat actor to hide something that would allow them to maintain persistence in the domain. And if we don't take care of that edge case, we may miss something critically important. To identify that, one option would be to enumerate access rights in order to find any deny access right, for example. But there are many edge cases to consider here, because it's possible to set explicit deny, but it's also possible to remove all access right granting access. So it's not sufficient to only look for denies. It will also be possible to hide the security descriptor, which contains the access rights. And so we would no longer be able to parse those. One solution, as implemented in Farsight AD, is to rely directly on replication operations, which are, as I said earlier, the operation used by a domain controller to replicate data. And by retrieving data this way, we are not impacted by access rights. To do that, I use code from Mimikatz and Make Me Enterprise Admin, which are projects that implement the desync attack more on the offensive side. So yeah, the code from the offensive side was used in this project. And if we now take a look at what kind of result we can get by importing the Farsight AD PowerShell script and executing the cmdelete to retrieve replication information, we will retrieve those attributes through a replication operation, and we will also retrieve them through direct queries. And we will check if we have the same level of information. If not, that means those attributes are hidden. And so as we can see here, we have both our fully hidden user with all its hidden attributes and our user with only a partial subset of attributes hidden. There is the SID history, and there is also the primary group ID that was actually hidden as well, but didn't make the cut for the previous demo. But yeah, by doing that, we can make sure that we have access to the right attributes and we can start looking for persistence. There are multiple techniques that can be used, lots of techniques. I won't have time to cover all of them. And I've divided those techniques in two categories. The first one are techniques that allow a threat actor to maintain authenticated access. And the second categories are techniques that can be used from an authenticated access to elevate privileges. There are, of course, some techniques that can be used for both. So there may be some overlapping here. We will start by looking at the techniques that can be used to maintain access, and we will take for granted that every user's and computer's password has been reset, and that the KBTGT and trust account passwords have been reset twice, in order to invalidate Kerberos tickets. The first technique here is based around the user principal name and all security identities attributes of a user that I will be referencing to as UPN and ALSEC ID attributes. Both of those attributes, as you may see on the certificate processing logic here, which is quite complicated, but doesn't matter too much to us. Those two attributes have an impact in the PKInit authentication flow. PKInit is authentication through private public keys in a Kerberos authentication. What's important to us here is that the subject file name of the certificate used for the authentication is mapped to the user UPN, if the user has an UPN, and can allow authentication that way. If the certificate has no subject file name, then some parameters of the certificate are used to be mapped with the user ALSEC ID. As a result, by modifying a user UPN or ALSEC ID, it would be possible to authenticate as that user using a certificate belonging to a completely different user. One thing worth noting here is that every time you do a PKInit authentication, you can conduct a subsequent Kerberos ticket request to retrieve the NT hash of the user. It's called unpack the hash. It's been put in the spotlight quite recently. And it's something that has been implemented by Microsoft to allow NTLM authentication following a Kerberos authentication, which would otherwise not be something possible. But yeah, for us, it means, well, or for threat actors, it means that by doing a PKInit authentication, it's not only possible to authenticate as your user, but also retrieve additional credential information and possibly the user password by doing some offline brute force attack. In order to identify persistence through a user principal name and ALSEC ID, we have to understand a bit more how those attributes are constructed. For the user principal name, it's quite easy. They are based around the user username or mail attributes. So we can query those and check whether or not there is an anomaly here. So it's relatively easy to spot something that seems not normal. For ALSEC ID, it's much more difficult, as it's some parameters from the certificate, and the fingerprint of the certificate is one of them. So it's very difficult to be 100% certain that a certificate belongs or not to that user. That's why if there is no definitive conclusion on that, it's generally advised to remove ALSEC ID entries. In FAIRSAT ID, the UPN are enumerated as well as the ALSEC ID, and some work is done to check whether or not the UPN seems legitimate. There are also timestamp retrieved through ID replication metadata to check whether or not those attributes were modified recently or in the time frame of attack, which can help us identify whether or not there is some kind of persistence going on here. Another technique that can be leveraged to maintain authenticated access is through an attribute known as a shadow credential, the MSDS key credential link. This attribute was added by Microsoft to allow public-private key authentication in an environment without a public key infrastructure. So it doesn't contain directly certificate material, but it contains what is called key credentials. We will get into a bit more of that later on. And those can be used to authenticate. This attribute has been put in the spotlight quite recently as a takeover primitive. So more for the lateral movement and privilege escalation part, but it can also be used to maintain persistence. So what we can do here is parse those key credentials, which are otherwise just a blob of data, not human readable, to retrieve more information on the key credential, on each key credential. Interestingly enough, we have a key created timestamp for each key credential, which can give us information on whether or not this key was added during our time frame of attack. There is also an approximate last timestamp of last use, but it doesn't seem to be reliably updated. So, well, there is a key created one, which is reliable, but the second one is more indicative. And last but not least, another technique that can be leveraged to maintain persistence is through certificates. It's the most obvious one, as any users or computer account can request a certificate for itself with a period validity of 1 year. So if a threat actor has compromised an account, they could simply request a certificate and use a certificate to authenticate, even following a password reset. And again, through the unpipe the hash technique, they could retrieve the NT hash of the account. What we can do here is we can try to look for all those certificates, check for the period of validity to check whether or not the certificates were recently generated. And we can also check if those certificates have subject all name, because as I said earlier, those subject all name can be used to authenticate as other users. So there could be some certificate associated with a low privileged user, actually allowing authentication to a much more privileged one. And yeah, what we do in FASAT AD is that we pass all of the certificates and we try to retrieve as much information as possible, as much timestamp as possible. But while certificate can be requested, they could also have been compromised in post-exploitation techniques. And so a threat actor may have compromised already existing certificates. If that's the case, well, it's usually recommended to renew the CIA certificate, root certificate, at least progressively, because it's something that would invalidate all the current certificates, not only for client authentication, but for example, also for server authentication, certificates used to do, for example, HTTPS access in the environment. If we now take a look at techniques that could be used to maintain a path to high privileges, so from an authenticated context this time, we have a few techniques there, notably Kerberos and constraint delegations, or Kerberos delegations that won't be covered because to follow the 40-minute time frame. But what we would be talking about are the SID and primary group ID persistence. But first, what does high privileges mean? There are some well-known groups, domain admin and enterprise admins, which gives us the possibility to do basically everything in the environment. But there are also other groups, sometimes not as well known, that have direct compromise paths to domain admin and enterprise admin privileges. There is, for example, the server operators, backup operators that can remotely connect to domain controllers and dump the NTDS Active Directory database. So even though those may not be considered from the start as highly privileged as domain admin and enterprise admin, they have a very quick and easy way to elevate the privileges. Okay, so now on the SID and primary group ID persistence. Whenever you authenticate on Windows, you get an access token. It's linked to your process, explorer.exe, for example, and this process is used for every operation you conduct. It really represents your security context. This access token, in the case of Kerberos authentication, is constructed using the service ticket provided to authenticate. The service ticket contains notably the primary group ID as well as all the SIDs in history you may have. So in the authentication flow, you first get a ticket granting tickets following your Kerberos authentication. You then get a service ticket from which the pack is added to your access token. And then whenever you access secureable resources, that is resources with a security descriptor, this access token is used against the access control list on the object. And every access right defines an SID, and there is a mapping there between the SID you have in your access token and the SIDs that are allowed to do operation on the object. If you are allowed to conduct the operation, you get the access you want. Otherwise, you get an access denied error. So for a persistence point of view, what you had in the SID history or what you had in the primary group ID will ultimately be used whenever you access resources. So it would be fully possible to impersonate a more privileged user by adding SID in history or by modifying your primary group ID. To look for persistence here, first on the SID history side, we can enumerate all SIDs in history and look whether or not they belong to the current domain. It should normally never be the case. SID history is normally used for migration purposes of users between domains. So there should never be any SID belonging to the current domain. And we can also check whether or not this SID belongs to a more privileged user. On the RID, primary group ID part, primary group ID have by default a value linked to the object type. So for example, for users, I have a precise RID, which should normally not change. So here we can enumerate those values, take for anything that's not default, and map those RID, so the relative ID, with group of the domain to check whether or not the RID is privileged. And as with every replicated attributes, we can retrieve timestamp from replication metadata to check whether or not the change was recently made. Okay, now if we take a look at the group policy object persistence, there would be quite a lot to say on GPOs. They are basically a way to deploy parameters or settings, either to users or to endpoints. They can be configured on organizational units, seat, or domain with a prevalence order, and the GPO, the closest to the user or computer being applied in case of conflicting conflicts. There can all be some kind of filtering going on with WMI filtering, for example, to only apply on specific hosts or users. But for us, whenever looking at persistence, it doesn't matter that much because we would rather have false positives than false negatives, right? And while it's quite complicated, it can also play to our advantage. There were a case where the attacker granted himself privileges to a GPO, a new created GPO. And by doing that, he overridden an existing GPO and removed access for legitimate administrators. And that's how the threat actor got caught. If we take a closer look at what can be defined through GPOs, there really is lots of settings. There can be logon rights or privileges. So for instance, the right to remotely connect to an endpoint and drop process memory. That would be one thing, for example. There can also be Active Directory domain level privileges that can be configured through GPO. So for example, the right to add a Kerberos delegation in the domain. There is a possibility to execute code in a number of ways through immediate or scheduled tasks, for instance, as well as by deploying logon or logoff scripts that get executed whenever a user log on, log off, or whenever the computer starts off or is shut down. And there is also the possibility to modify the registry directly by setting registry keys. One thing interesting here is that the GPO files, so the part of the GPO that contains the settings as files, directly as files, are normally stored on the sysvol directory on domain controller, which is a replicated directory, but they could also be stored on something entirely different as long as the endpoint have access to that folder. And so there would be a way for threat actors to change what the GPO does simply by modifying files they have write access to. And yeah, that's something that would make incident response here a bit more difficult, because if we don't have access to the file, well, we may know that it's illegitimate, but we would have no way of knowing what was done through that GPO. So in Fairsight AD, there is two commandlets aimed at uncovering GPO persistence. The first one looks at access rights granted on GPOs and GPO files, as well as when the GPO was created, whether or not the GPO is linked and applied to a privileged object. So this one is most of a first look to have a first understanding of the GPO configured and try to then focus our analysis on specific GPOs. The second one, sorry, is a bit more complicated and parses the GPO files to retrieve a number of settings. So for example, it will retrieve and parse the XML files configuring immediate or scheduled tasks to have an understanding of what the GPO is executing. It will also look at which privileges are granted through GPO and whether or not those privileges may allow remote access or may allow a threat actor to conduct privileged operation on the endpoint. So yeah, there is a number of settings configured there. Some things are very hard to fully and comprehensively parse. For example, registry keys, because there could be dozens or dozens of possible ways to execute code to registry, of course. But it can give you a good first understanding of whether or not the GPO seems malicious or not. Another well-known way to maintain persistence on a domain would be through access rights. There are some well-known access rights there, such as the generic all or write DSCL access rights that would allow all operation to be conducted on the objects. But there could be also some specific edge cases, such as the right to modify specific attributes of a user or computer account. So for example, a threat actor could grant himself the right to modify the UPN or ALSEC ID attribute of a user to later on authenticate as that user by first setting the attribute value to a certificate he has access to. And there can also be some specific access rights, such as the one to conduct replication operations. So for example, as used in DSync attack, so to retrieve secrets, or the access rights that would allow the DC shadow attack, which is the attack that was used to modify an SID history. So there is a lot of edge cases to consider here. And those privileged or dangerous access right could be configured on a number of privileged objects. There is a well-known admin as the holder container, of course, whose SCL access rights are replicated to privileged objects, but it doesn't cover every privileged object. There would be, for example, domain controllers, machine accounts, domain controller groups, which are not protected. And so there would be also a number of privileged access to review. And that's where automation really shines. So in Fairsight AD, there is two possibilities to help uncovering A-shield-based persistence. The first one is by reviewing the access rights configured only on privileged objects. The second one on all the objects in the domain, and to filter or highlight dangerous access rights. So with a list of hard-coded access rights that may not be comprehensive, of course, because there could be edge cases not considered. It can take a lot of time and be quite time consuming, especially in a forest recovery procedure where we have to move fast and provide results fast. So a second option is to restore the ACL from their default values. The default values are retrieved from the schema, the Active Directory schema at the forest level, and are linked to the object-specific class. It would, however, be possible for a threat actor with enough privileges, of course, to modify those ACL, and so replicating or restoring ACL from their default value would not be enough to eradicate persistence. So that's why there is a commandlet in the Fairsight module to verify if the ACL are actually into their default states based on the Microsoft documentation, and to highlight a possible dangerous access right if that's not the case. Okay, so in conclusion, as you may have seen, identifying ID persistence is hard, and automation has its limits because there are lots of edge cases to consider, and there may be cases where what could be persistence may actually be the result of legitimate administrative actions. Something also very important in a forest recovery procedure is that persistence or privilege escalation path could already be present in the environment. So looking at timestamp, matching the time frame of the attack is not enough. There should be a review of all the possible compromise paths to make sure the domain is more secured than before the attack. So not only going back to how it was before the attack, but also making sure that any compromise path that could have been exploited by the threat actor is remediated. And last point, AD backup isolation is really important, especially for ransomware attack. It's much more easier to go from a state that is presumed to be good rather than trying to find persistence in a state that is known to be bad, right? So yeah, making sure it's properly isolated, not domain joined, and that there is some testing going on to make sure that the backup can be actually restored. There have been a number of techniques that could not be covered in this talk, but there are more content in the deck if you want to take a look at, for example, Kerberos persistence. And if you have questions, feel free to ask them in the Slack, and I will try to answer as much question as possible.